So we just finished sample problem 19.6, which we kind of call a type 1 problem, where we're given equilibrium concentrations of ions in solution as we define as X in terms of the solubility in water, and we use those equilibrium concentrations to calculate a KSP value. In sample problem 19.7, now we're going to use an established KSP value and then calculate the equilibrium concentrations. We're going to calculate the solubility of a salt in solution. So this is kind of what we refer to as one of those type 2 problems. So we're going to treat it the exact same way we treated type 2 problems that we had in solution with in chapter 17. First thing we want to do is write an equation. So they tell us calcium hydroxide, a major component of mortar, plaster, and cement, and solutions of calcium hydroxides are used in industry as a strong, inexpensive base. Despite that, though, calcium hydroxide is not completely soluble like something like sodium hydroxide is, and the KSP is listed as 6.5 times 10 to the minus 6. So because it's not completely soluble, it's only slightly soluble, it means that when we have some solid calcium hydroxide, it only dissociates partially into its calcium ions and then 2 hydroxide ions. KSP we can define as the concentration of calcium times the concentration of hydroxide squared, and they give us a value for this, 6.5 times 10 to the minus 6th. Now, one of the things that's important to talk about is the calcium hydroxide amount is irrelevant as long as the solution is saturated. Okay, so what this really means, I just want to draw a little picture down here. We've got a flask maybe that we've put a chunk of our calcium hydroxide in. And what's going to happen is some of that is going to be allowed to break apart and make some calcium ions in solution and hydroxide ions in solution. And as long as we still see some of this down below, we know that we're going to have calcium ions in solution, and we're going to have those in ratio to the hydroxide ion concentrations in a 1-to-2 relationship, because we can see that for every formula unit of calcium hydroxide that breaks apart, for every 1 mole of this that breaks apart, we get 1 mole of calcium ions and 2 moles of hydroxide ions. So in this problem, when we start with a chunk of something here, we're going to get a 1-to-2 ratio of the ions in solution, and as long as we still have some of the solid down at the bottom, we're going to know that we put the maximum amount of those ions in solution, and we're going to define that then as the solubility. Okay, so we need to see what that maximum solubility is going to be, and for that we use an ice table. Solids, again, don't appear in our ice table. We're going to assume for this problem no other sources of calcium or hydroxide ions. This breaks apart, again, in a 2-to-1 ratio here of hydroxide to calcium. So we get X and 2X. One of the nice things that we have here is because this guy is not anything that was part of our equilibrium expression, is we have no assumptions that we need to worry about. So KSP here is going to be equal to X times the quantity 2X squared, and that's equal to 6.5 times 10 to the minus 6th. Solving for x, we get 4x cubed equal to 6.5 times 10 to the minus 6th. X is then equal to 1.2 times 10 to the minus 2nd molar. And again, that's equal to the calcium concentration. And so if we double that, we'll get the concentration of hydroxide. So this problem didn't ask for that. This problem asked for the molar solubility. And when it asks for the molar solubility, it's really asking you, what is X? So X happens to be equal to the calcium concentration, but since that's also equal to, essentially stoichiometrically, this value in our equation, X is also equal to, or we define it as, the molar solubility. Okay, so the molar solubility is going to be 1.2 times 10 to the minus 2nd molar. So the molar solubility of calcium hydroxide is 1.2 times 10 to the minus 2nd. So again, just to remind everybody that when we have a problem like this where we put a chunk of something in solution and then we allow it to break apart, In this case, we're going to have a ratio of concentrations that's 2 to 1. We define the molar solubility as 1.2 times 10 to the minus second. So again, as a check, if you take 1.2 times 10 to the minus second and you multiply it by 2.4, which is going to be the concentration of hydroxide, times 10 to the minus second, and you square that, that will equal 6.5 times 10 to the minus 6. We always have that internal check to go back and check our equilibrium problems. Just as a little heads up, one way that I could make this problem a little bit more interesting and a little bit more applied is I could ask you, what's the pH of this solution? Because you're going to be able to obtain the concentration of hydroxide, here's the concentration of hydroxide in this solution, you can use the negative log of that to figure out pOH and then from there get pH. So kind of a more applied way of this is thinking about what the pH of this solution would be. So as you're working through problems, always kind of think if there's a new way that Dr. Parenti could ask this problem or a new application that I could make.